Hello friends. Previously, we began the discussion on the hydrogen atom. Specifically, we want to find the energy states of an electron bound to a nucleus by the Coulomb potential. That is, we are trying to solve this energy eigenfunction equation. The solutions of this equation are separable into a radial part and an angular part. Each depends only on a subset of the spherical coordinates. The angular part are the spherical harmonics that are just eigenfunctions of angular momentum. All these have been established in Lecture 10. We shall not comment further about the spherical harmonics as they have been thoroughly discussed in the previous lectures. Watch them first if you are unfamiliar with this topic. This time we focus on the radial function r. This satisfies the radial equation, which can be separated from the full equation in the yellow box using the separable form of psi. Capital R itself can be expressed in terms of a new function, u, as we have shown in the last lecture. Substituting this into the radial equation gives an equation for u, where we have replaced the radial coordinate r with a dimensionless variable ρ. This equation can be reduced further if we use the following trial solution for u, which separates out the behaviors for small and large radial distances in an explicit way. A new indeterminate function f then characterizes the behavior of the wave function for intermediate radial distances. This function must satisfy the equation in the blue box. We have proposed a power series solution to the function f rho, and this results in the following recursive relation for the indeterminate coefficients a's. This is where we stopped in the last lecture. Before we proceed any further to more detailed calculations, we might first wish to estimate the asymptotic behavior of f, as suggested by this recursive equation. Let's examine the coefficients associated with high powers of ρ, and take the limit of the summation index s going to infinity. The ratio of two consecutive coefficients goes as follows. In the limit of large S, this approaches Notice that this ratio is positive. This suggests that terms of higher powers in the variable ρ add up in a constructive superposition. Therefore, these terms of the series dominate as ρ goes to infinity. Let's use this recursive relation to relate as to as minus 1. We can keep on applying this relation until we reach some minimum value s0, which is the smallest value of s considered to be large powers of ρ. This criteria need not be exact, as we are merely doing an estimate. Let's assume that it takes m steps to reach as0, so there are m number of terms in front. Let's evaluate this prefactor. First, we can collect together all the factors of 2. Note that m is simply s minus s0. Then we insert the factorial of s0 minus 1 divided by itself, such that the denominator can form the complete factorial of s minus 1. All the terms that are dependent on the summation index s is collected in the red box. And this takes the following generic form. B is some constant which is taken to be arbitrary, What's important is that it is very much smaller than S. The factor independent of S is collected as the constant A. Let's substitute this back into the power series. Notice that we have started this sum at S0. This is reasonable because we are just trying to approximate the behavior of the function in the region of large rho, where the dominant terms are the large powers. Let's shift the powers in the numerator so that it matches the argument of the denominator. Since the sum is over all indices that are very much larger than b, let's just drop b. We can also start the sum from 0, since this will only include negligible terms in the limit of large rho. Then the series in the red box is just an exponential function. This creates a problem for us, because this implies that the function u is not normalizable, but in fact blows up exponentially at large rho, which means the integral of the absolute square of u is not finite. Recall that in the last lecture, we specifically avoid this solution in the asymptotic limit of large rho, and chose the exponentially decreasing solution instead. All these suggest that the function f cannot be an infinite series and must terminate after a finite number of terms. That is, it should be a polynomial of some maximum degree S max. We can figure out the conditions such that the series will terminate at a given value, S max, by looking at the recursive equation, and see how the coefficient A associated with one power above this maximum power might vanish. This implies that the numerator on the right hand side must be 0. We can write this as a condition on xi. Notice that all the terms on the right hand side of this relation are positive multiples of 2. This means xi is an even integer. N is a new integer parameter that now labels xi. We claim that this equation implies that energy is quantized. That is, they exist as discrete levels. We shall prove this shortly. But first, let's continue with our computation of the polynomial f rho. We would need the recursive relation again. Shift the index as like so. And we get a more convenient expression. This will allow us to work backwards, starting with any power down to a0. We can express minus xi plus 2l in the red box in terms of S maximum using the first equation at the bottom. The multiplicity of the angular momentum quantum number L can be replaced by the notation alpha, just to tidy things up a bit. As-1 can then be related to As-2 one step below by applying the recursive relation again. We can keep on doing this until we reach a0. will take s number of steps to get from as to a0. Just look at the terms in the denominator that are highlighted red to figure this out. We can gather up all the factors of minus 2. Next will be the terms highlighted red in the denominator. They look like s factorial. How about the rest of the denominator? We can complete this factorial by multiplying then dividing by the factorial of alpha. Since this term is in the denominator, let's flip this upside down. Now we can look at the terms in the numerator. Notice that these terms are decreasing towards the left in steps of 1. So we can again complete the factorial by adding some extra terms to the left, similar to previously. The terms in the red box are just the factorial of s maximum. This is already looking much more compact. Let's simplify this a little more by organizing some of the factorials into a binomial coefficient. Using the old trick, notice that in the red box, the argument of the factorial in the numerator is just equal to the sum of the arguments in the denominator. This is just what a binomial coefficient should look like. The rest of the terms are independent of the summation index s and could be absorbed into the normalization constant of the wave function. So let's just drop them. The powers of 2 can be grouped with those of rho. This is what is known as a generalized Laguerre polynomial, in a form you will find in Wikipedia or most mathematical handbooks. In its superscript is the multiplicity of angular momentum, and in the subscript, S max. Let's change the notation from S maximum to D for degree. To familiarize ourselves with this function, let's quickly look at some examples. For degree 0, f is obviously a constant, and by the equation below, this corresponds to n equals L plus 1. We shall explain why the number n is important in a minute. It turns out to be the discrete index of quantized energy. By the convention in the yellow box, f is equal to 1. For the case of degree 1, n increases by 1. The relevant binomial coefficient is given by expanding this out. Two indices are relevant for degree 1, s equals to 0 and s equals to 1. Thus we have F rho for degree 1. Let's compare this with Weinberg's book. They agree up to normalization constant. We now show that this condition, which determines that the power series for F terminates at power d, also predicts the quantization of energies within the hydrogen atom. Let's now calculate the energy eigenvalues. Recall that xi is a dimensionless parameter defined like so. Let's make kappa the subject of the formula. Kappa itself is defined like so, in terms of energy E. Let's make this the subject of the formula. We can eliminate kappa squared from the second equation using the first equation. Let's replace xi with 2n. Thus we have shown that energy is quantized. N is what is known as the principal quantum number and labels the energy. This agrees with the result derived by Niels Bohr using his rather ad hoc theory of electron orbits in 1913. Here we derived it with the fully developed formalism of quantum mechanics. Looking at the equation in the blue box above, we can conclude that n is an integer starting from 1. This equation also allows us to figure out what are the allowable values of L for a fixed value of n. The upper limit of L occurs when d equals 0. Now we can calculate the total number of distinct states with energy En, that is, its degeneracy. The total number of values of L within this range is n. Note that L itself is degenerate and consists of 2L plus 1 possible values of M. This was shown in lecture 11. Let's count the number of states with energy En. So the degeneracy of energy for an electron bound to a hydrogen-like nucleus is n squared. This will be important in describing the structure of the periodic table, as we will do in chapter 4. Here's all the essential equations we have derived in this lecture. Basically, we have solved the energy eigenvalues and eigenfunctions for an electron in an atom. These are simultaneously the eigenfunctions of the mutually commuting observables, energy, the square of angular momentum, and the third component. In the next lecture, we shall examine the physical consequences of these equations.